Hello there. Welcome to my second lecture series brought to you by the coronavirus and St. Patrick's Day edition. I got my green vest on. I'm not letting the virus get my Irish spirits down. I'm going to take out this lecture. It's going to be a good time. First things first though, if you're here from CSC498, check that video title. It's up here, somewhere around here. Make sure you read those video titles because you could be in the wrong course. This is CSC498 Stochastic Modeling. You're of course welcome to stay, but if you start seeing the material and you're freaking out because you don't know what's going on, that's probably why. Okay, so CSC498 Stochastic Modeling. What was the first thing, what was the last thing we looked at? Well, we were looking at Jackson networks. Jackson networks. What were those? Well, there's two types of Jackson networks. The first type is the open Jackson network. And with Jackson networks, it's just a series of queues hooked up with each other. And when I say an open network, I mean jobs can arrive from outside. So we might have something that looks like this. We have one queue, two queue. Hey, maybe we have a third queue. And we have jobs that arrive from outside. But we could also have these queues hooked up with each other in certain ways. Maybe this one comes down here, or maybe it goes over here. And what were some of the rules on the Jackson network? Well, the first rule is everything's exponentially distributed. So the arrival streams from outside the network, those are Poisson processes. Remember, Poisson processes have inner arrival times that are exponentially distributed. What's the other constraint following the exponential distribution? That's right, the service times. The service times at each one of these nodes is going to be exponentially distributed. Do we have anything else required or any other constraint imposed on these networks in order to qualify them as a Jackson network? Yeah, there was one more thing. What was that? Well, it has to have what we call probabilistic routing. So when we have a choice of where to route, we have a straight up probability here. And there's another choice here. Maybe it only leaves with 0.1, 0.9. So what this means, if I leave this queue with a 10% chance, I leave the network, and with a 90% chance, I go back to this node over here. That's probabilistic routing. Something that wouldn't be probabilistic routing is, okay, the first job leaves, the next job goes here, the next job leaves, the next job goes there. Something like round robin, where it's a little bit more deterministic, less variance. This is purely probabilistic. Okay. Well, with open networks, it turns out we can do some nice analysis, and it's definitely solvable because we get this key result where, look, each one of these queues, they're not quite MM1 queues. They don't behave like MM1 queues. However, in steady state, they do behave as MM1 queues. And it was actually a pretty fantastic result because we can get things like response time, expected response time, expected number of jobs at each node. You can get the probability of jobs being at certain nodes. And you get this nice product form solution, that's what we called it, and it just works out. So on the open Jackson network side of things, because in steady state every node rather, behaves like an MM1 queue, things are relatively easy, relatively straightforward. So that's the first type of Jackson network that we looked at. What was the second type? Well, I mean, pretty obvious. If you have an open network, what's the second type of network that you might have? Closed. So a closed network, Jackson network, follows all the same constraints. Everything's still exponential. All the service times are exponentially distributed, and all the routing is done probabilistically. Okay. Well, what's different? Well, here we have jobs arriving from outside the system, and we have jobs eventually leaving the system. With a closed system, jobs never arrive, they never leave, they just circulate. So we always have a constant number of jobs in a closed system, and they just circulate through the system. So we might have something that looks like this. You see, I have no arrivals coming from outside the network. I have no arrows leaving the network. They just constantly circle through this closed Jackson network. Okay, and again, I have probabilistic routing, so maybe I have 0.4 here, 0.7 here. And last time we started analyzing this, can we analyze the closed Jackson network? Answer is yes. Why can we analyze it? Well, we have a fixed number of nodes, fixed number of jobs in the system, and everything's exponentially distributed. Well, if everything's exponentially distributed, if you choose your state space correctly, you can create a continuous time Markov chain that models the system. What's the state space? Well, it's going to be the number of jobs at the first node, number of jobs at the second node, number of jobs at the third node. And if you have k nodes, it's going to be a k tuple. Okay, and because I have a finite number of jobs circulating through there, there's a finite number of combinations, a finite number of states in my Markov chain. Well, that means I can theoretically solve my Markov chain, get the steady state distribution, and I can answer things like, what's the expected number of jobs at the third node? What's the expected response time of the first node? What's the probability that there's at least 3 jobs at each node? Or what's the probability that there's exactly 2 jobs at the second node? Things like that. It allowed me to answer questions like that. Well, if I can analyze closed Jackson networks, what are we doing here? Why am I giving this lecture? Well, there's a little bit of a problem with that. What was the problem? Well, okay, if I directly solve the Markov chain, I get something like this, complexity-wise. So on what order? And I shouldn't be using big O because it's not quite an upper bound. It's actually a lower bound. So how many states do I have in my Markov chain? Well, it's basically how many ways can I arrange n jobs on k nodes, and it's like those, how many ways can I arrange n books on k shelves, those combinatoric questions, and you end up getting something like this. If I have n jobs and I have k nodes, I'm going to have another bracket here, n plus k minus 1, choose k minus 1, complexity. So that's how many systems of equations, that's my states I have, that's going to yield that many equations, and I have to square that essentially to solve my Markov chain. That's a little rough. It turns out we could do a little bit better, and we looked at it, well, what if I do like this product form solution? And you can check your notes that we did some of that analysis last time. Remember we solved like those fake lambdas. Based off those fake lambdas or those fake arrival rates, we got the real steady state distribution, and we can work back to then recover the real lambdas. And doing it that way, we didn't have to solve a system of equations, but you still have this combinatorial explosion. So you still get, this is way 1, this is way 2. You still get n plus k minus 1, choose k minus 1 complexity. And as k gets large and as n gets large, that blows up. It's not good complexity. But this gives us all the fine-grained information. Like I was saying, this gives us steady state probabilities or the steady state distribution. This one also gives us steady state. And we can get things like expected response time, expected number of jobs in the system. Same with this way down here. Okay, well, is there a third way? And hopefully, well, there's probably lots and lots of ways to do it, but I want this third way to have better complexity than these two things. Than this basic combinatorial state space explosion that we'd see if we try to handle it either with the Markov chain or some kind of product form solution. Well, it turns out there is. Oh, look who's here. Come to learn some combinatorics? Come up here, bud. Up. Yeah. Oh, you want to say hi to the class? Come here. You're going to say hi. Oh, you're a tank. Give kisses to the class? No? Oh, good boy. Oh. All right, but I got to get back to work. I know. You can watch if you want. Oh. All right, where was I? Is there a third way? Well, yes, there's many ways. Many ways we can solve this thing, but I want a more efficient way. Well, there's something called mean value analysis. Okay, Mean value analysis. Well, it turns out this is going to run, hopefully, if we do it correctly, in nk time. Well, that's way, way better than a combinatorial explosion here. We get like a polynomial solution down here, pseudo-polynomial. Okay, well, it seems like it's just better than the other two, if this is true. Well, I mean, in general, you might say it's better, but here's the thing. We cannot, using this method, solve the steady state distribution. So what do I mean by that? Well, using mean value analysis, we will not be able to answer things like there are exactly 3 jobs at the second node, or what's the probability that there's 4 or more jobs at the first node. We can't answer questions like that. What can we answer? Well, up here, it's mean value analysis, so it's going to allow us to get the expected response time at the ith node. I'm going to use a subscript I to denote the expected response time of the ith node, the expected number of jobs at the ith node, and one last thing, we're going to be able to calculate the utilizations of each node. So it's useful information. It's really kind of the information that we usually are interested over here, but it's certainly less information available to us using mean value analysis compared to these two other ways, the Markov chain or the product form solution. Okay, well, what's mean value analysis? Before we get into mean value analysis, we need to define a few more things and have a little bit more, a few more observations. So, well, you know what? I have to be careful with my whiteboard space. I have so little of it, and I want to keep at least that second network up on the board. Okay, I'm going to hit you up with a theorem right here. Something called the Arrival Theorem. This is going to be true for Jackson networks, open or closed actually, but it's going to be more useful to us closed. The Arrival Theorem. A job arriving to a node in a Jackson network sees the system in steady state. Hold up, let me finish. In steady state with 1 fewer jobs. So my writing gets messier the lower I get down, because I have to crunch down here. But what does this mean exactly? Well, if I have 10 jobs in the system, assume I'm working with a closed Jackson network, I have 10 jobs circulating, and the job leaves whatever node it was processed at, and it goes and arrives at a new job. That's an instance in time. That's a precise moment in time. It just arrives to a new node. If it looks around the system, checks things out, remember there's 10 jobs total in the system, but if that job looks at every single node, it's going to see the steady state behavior of the system as if there were 9 jobs in that system. So that's pretty weird. And there might be some intuition for it, but it certainly isn't obvious, and it almost shouldn't be expected. For instance, most networks or most systems, that's nowhere close to true. And you can convince yourself, just set up a simple network and make everything deterministic. This certainly will not hold. So why does it hold? Well, it kind of comes down to, remember I told you in the beginning of this course, basically everything is going to follow the exponential distribution and be related to the exponential distribution and the memoryless property in some way. This just happens to be another one of those magical results that just seems to drop out of the exponential distribution. Remember, everything's exponentially distributed over here. But it's definitely a boss result. Certainly going to be useful for us moving forward. Okay, So that's the arrival theorem. I'm just going to hit you up with one last piece of notation, and then we can get to building up this approach. The dog left, he got bored. Right? See, like when the dog gets bored, he can just leave. I'm sure plenty of you would like to do that in lecture, but I mean, maybe some of you do it, to be honest, but yeah, he wasn't having it. Okay, one last piece of notation. PI. What's PI going to denote here? Well, given a job just arrived to a new node, PI is the probability. I'm misspelling everything today. Is the probability that that job. So my 363 students know this already. Might have to tell you 498 guys. I'm going to be in the way when I'm writing stuff. There's not a lot of room down here. I mean, we got to deal with the resources we have. It's not like the worst, but certainly not the best. But I mean, that's the world we live in, okay? The probability that that job arrived to the ith node. Okay, so PI. Given a job just arrived to a new node, so some job, doesn't matter what job, it just arrived to a new node, and PI is going to denote the probability that that job arrived to the ith node. So P1, for instance, is the probability that given the job arrives to a new node, it arrives to this first node. And you can kind of even look at this network. If I told you a job just arrived to any of these nodes, or a node in general, you should have a pretty strong intuition that this first node has a higher probability of that job arriving to it than these ones. Why? Well, every single job that leaves either of these goes here, and only a portion that leave these go to either of those. So that's the intuition behind it, but you can actually solve this, formally. So let's try to solve these PI values. And in order to solve the PI values, we need to solve the visit ratios for the system. So V1, V2, and V3. This is the number of visits to the first node, some number of visits to the second node, number of visits to the third node, based off some kind of normalization or reference node that we'll get into a little bit later. But here's the idea. If I let V equal the total number of visits, so that's V1 plus V2 plus V3, then PI is going to equal VI over V. Because you can think, okay, well, P1 is going to be the number of visits to V1 over the total number of visits. That's going to be the portion of visits to the first node. That's the probability that given a job arrived to a new node, it's going to arrive to the first node. That's the proportion of visits that arrive to that node. Well, that's going to be the overall probability that that job arrives to that node. Okay, not bad. So I just have to solve for V1, V2, and V3. Well, how do I do that? Well, I look at this. For every visit to this node, 0.4 of those visits are going to go to this node, and I guess I should label these nodes. I kind of intuitively did in my mind, but this is going to be node 1, 2, and 3. Okay, well, what's the number of visits to node 2 here? It's going to be the number of visits to this node, 40% of them. Okay, well that means if there's 10 visits to this node, it's going to be roughly 4 visits to this node. And I can express that mathematically, of course, as V2 equals 0.4 V1. What's V3? Well, same logic. 0.3? Don't think so. 0.7 V1. Well, what's V1? Well, I just look at the arrows going into it. 100% of the visits from V3 and 100% of the visits from V2. Well, that's going to equal V2 plus V3. So if you take a moment and you try to solve that equation, or set of equations, what you'll find is there isn't a unique solution to it. There's an infinite set of solutions. These equations aren't homogeneous, or they aren't heterogeneous. Meaning there's an infinite number of solutions to this particular set of solutions. Well, how are we going to cope with that? Well, here's what we're going to know. Check this out. You know, I have an infinite set of solutions here. What if I just choose one? What happens? What do I mean by choose one? Well, I'm going to say V1 equals C. Okay, equals some constant C. That's going to yield me one of these infinite solutions to this set of equations. Well, that implies, of course, that V2 equals 0.4C and V3 equals... Okay, so I just noticed straight up, probably on the board since the beginning of lecture. Yes, you guys have been laughing at me, I'm sure. What mistake have I made? 0.4, 0.7, what does that add up to? 1.1? That doesn't make any sense. So, there's something probably in the back of my mind when I made that 0.3 error. You know, you gotta listen to those processes in there. So let's just change this to 0.3, because these probabilities have to add up to 1. How am I gonna change this? Well, just go back and correct. And you see, doing these lectures online, I could go back and redo this entire thing and pretend like I didn't make that error, but that's just way too much work. There's no way I'm going to do that. I'm just going to have to suck it up and own that error. Okay, so 0.3C, 0.7C. Let's just throw this stuff into this equation and see what happens. So what if I want to solve for P1? Well, that's going to be C divided by C plus 0.3C plus 0.7C. Well, what happens? Yeah, of course. The C's cancel out. I can factor out a C here. C cancels out and I get 1 plus 0.3 plus 0.7, that's 2. Well, what does that mean? Well, first of all, it means that the probability of a job arriving to node 1 is 50%, but it also means that no matter which one of those solutions, infinite set of solutions I have to my set of equations, no matter which one I choose, these probabilities are going to be independent of it. Remember, C is just a general constant here. No matter which solution I happen to choose, P1 is unaffected, meaning these p-values, these probabilities, are completely independent from my choice. Okay, well that means I can, not necessarily have a unique solution to this set of equations, but I certainly have a unique solution to these probabilities. So we'll pause there. In the next video, I'll show you the mean value analysis algorithm. Thanks.